This topic is about infrared spectroscopy and mass spectrometry. So, spectroscopy it is the study of interactions of light and matter. Many types of spectroscopy rely on ability of atoms and molecules to absorb or emit the electromagnetic radiation or EM radiation. The absorption or emission of different forms of EM radiation or electromagnetic radiation is related to different types of transitions. Spectroscopy, a very fundamental tool of scientific study with application ranging from materials characterization to astronomy and medicine. Spectroscopy techniques are commonly categorized according to the wavelength region used, the nature of interactions involved, or the type of material studied. Again, spectroscopy, the study of absorption and emission of the light and the radiation by matter. It involves the splitting of light, or more specific, the electromagnetic radiation into its constituent wavelengths. Constituent wavelengths or a spectrum, which is done in much the same way as a prism splits light into a rainbow of colors. So here are the 5 different types of spectroscopy. First is ang infrared spectroscopy or spectroscopy. Second, the ultraviolet visible spectroscopy. Then, the nuclear magnetic resonance spectroscopy, the Raman spectroscopy, and lastly is the X-ray spectroscopy. So electromagnetic radiation or light exhibits both waves like properties and particle like properties consequently. Electromagnetic radiation can be viewed as a particle when viewed as a electromagnetic radiation consists of perpendicular oscillating electric and magnetic fields. For wavelength and frequency, the wavelength describes the distance between adjacent peaks of an oscillating field, while ang frequency it describes the number of wavelengths that pass a particular point in space per unit time. Accordingly, a long wavelength corresponds with a small frequency and a short wavelength corresponds with a large frequency. This inverse relationship is summarized in the following equations where frequency and wavelengths are inversely proportional. Now, the constant of proportionality is the speed of the light. When viewed as a particle, electromagnetic radiation consists of packets of energy called photons. The energy of each photon is directly proportional to its frequency. On the electromagnetic spectrum, it is the range of all possible frequencies is known as the electromagnetic spectrum, which is the arbitrarily divided into several regions. So here, makita dito sa example, ang vibrational energy levels for a particular bond are separated from each other by an energy gap. Pag ang photon of light processes exactly this amount of energy, the bond can absorb the photons to promote a vibrational excitation or an excitation. The energy of the photon is temporarily stored as a vibration energy until it is released back into environment, usually in the form of heat. Each form of spectroscopy uses a different region of electromagnetic spectrum and involves a different kinds of excitation. In this chapter, we will focus mainly on the interactions between molecules and IR radiation, which promotes vibrational excitations of the bonds in a molecule. So here, the signal characteristics of a wave number. So when we say infrared or IR spectroscopy, it is an absorption method widely used in both qualitative and quantitative analysis. The infrared region of spectrum includes electromagnetic radiation that can alter the vibrational and rotational states of covalent bonds in organic molecules. IR spectroscopy theory ang mag-utilize sa concept that molecules tend to absorb, specifically frequency of light that characteristics of corresponding structures of molecules. We also need to familiarize this one because infrared spectroscopy it is a very important technique in chemistry since it is an easy way to identify the presence of certain functional groups in the molecules. So for vibrational excitation, so makita diri ang example kung paano mag-vibrate, kung paano mag-excite. Example. So there are many different kinds of vibrational excitation because bonds stored vibrational energy. A number of ways bonds can stretch, very much the way a spring stretches, and bonds can bend in number of ways. The identifications of fundamental groups with IR spectroscopy. Each and every bond in a molecule, the energy gap between vibrational states is very much dependent on the nature of the bond. For example, the energy gap for a CH bond is much larger than energy gap for a CO bond. Both bonds will absorb IR radiation but ang CH bond lang ang mag-absorb with a higher energy photons. Walag mas taas ang energy gap ni CH bonds than CO bond, both lang gyapon sila mag-absorb og IR radiation. However, of course, ang CH bond lang gyapon ang mag-absorb of higher energy photon. In fact, each type of bond will absorb a characteristic frequency, allowing us to determine which type of bonds are present in a compound. We simply irradiate the compound with all frequencies of IR radiation and then detect when frequencies were absorbed. For example, a compound containing an OH bond, it will absorb a frequency of IR radiation characteristics of an OA bond. In this way, IR spectroscopy can be used to identify the presence of fundamental groups in a compound. The general shape of an IR absorbance spectrum. For examples, picture. So an IR spectroscopy measures the percent transmittance as a function of frequencies. This plot is called absorption spectrum. So kini tanan signals are all called absorption bonds. A point down on the IR spectrum. Hooke's law. For every bond and wave number of absorption associated with bond stretching is dependent on two factors. First, kay ang bond strength, and then second, the masses of atoms sharing the bond. The impact of these two factors can be rationalized when we treat a bond as it is where vibrating spring connected to weight. So using this analogy, we can construct the following equation derived from Hooke's law, which enables us approximate the frequency of vibrations for a bond between two atoms of mass, the M1 and M2. So in this equation, the F, the force constant of the spring, which represent the bond strength of the bond, and is the reduced mass of the system. Use of reduced mass in this equation allows us to treat the two atoms as one system. Notice that appears in denominator. This means that smaller atoms give bonds that vibrate at higher frequencies, corresponding to a higher wave number of absorption. For example, comparing the following bond, the CH bond involves the smallest atom and therefore appears at the highest wave number. Next is the effect of hybridization states on a wavelength of absorption. So in this section, we saw the bonds to hydrogen such as CH bond appears the left side of an IR spectrum or a wave number. We will now compare the various kinds of CH bond. The wave numbers of very much dependent on the hybridization state of the carbon atoms. Compare the following three CH bonds. So for signal characteristics, intensity, here the examples picture the comparison of a strong signal and a weak signal of an IR spectrum. So an IR spectrum, some signals will be very strong in comparison with other signals on the same time. Spectrum, that is, some bonds absorb IR radiation very efficiently. So the strength of a dipole moment changes when a bond is vibrates. Recall that a dipole moment of A bond is defined by this equation. So for analyzing an IR spectrum, when analyzing an IR spectrum, the first step is to draw the line at focus on any signals the left of this line, the diagnostic region. Now, what is the purpose of analyzing an IR spectrum? Reason for this one is because it is used by a chemist to determine the functional groups in molecules. IR spectroscopy measures the vibrations of atoms, and based on this it is possible to determine the functional groups.